Today we're going to talk about the third major conservation law that we're going to learn about this year, and it's a very important one, conservation of angular momentum. We're going to start at a very familiar spot here, and this is going to be Newton's second law for rotation. Net torque is equal to I times alpha. Replacing alpha with change in omega over time, then we have net torque times delta t is equal to I times the change in omega. I times omega, we have already learned, is equal to the angular momentum. So we have then the net torque times the change in time is equal to the change in angular momentum. And again, we've seen this before. And this only works when we've got a constant net torque and we don't have any changing I. So when we've got this, this is kind of the angular equivalent of impulse momentum. The torque times time would be the angular impulse, and then we have the change in angular momentum here. But something special happens when our net torque is 0. So if that is the case, then the left-hand side of this goes to 0. And so we have 0 is equal to the change in the angular momentum. And breaking change in angular momentum down to L final minus L naught, we end up with L naught is equal to L final. And that is a very important consequence. But we have to remember that in order for angular momentum to be conserved, then if net torque is equal to 0, we need that condition to be satisfied. All right, the net torque acting on the system has to equal 0. There can be some internal torques. One thing is applying a torque to another, the other thing applies that torque back, Newton's third law. But that internal torque has to cancel. The net torque acting on the system must be 0. So let's take a look at some examples where angular momentum is conserved. So here we have some small disk rotating with an initial angular velocity omega 1, and it has a rotational inertia I1, and we drop that disk onto another one that is initially at rest. Now, there is friction between the two disks. There is a frictional torque, and that frictional torque is going to slow down disk 1. It's going to speed up disk 2. So disk 1 applies a torque to disk 2. Disk 2 applies an equal and opposite torque back on disk 1. That is an internal torque. And when we consider the system as a whole, the net torque is 0. So if the net torque acting on the system is 0, then we can say that angular momentum is conserved. So L naught is equal to L final. Breaking that down, we'll say I naught omega naught is equal to I final times omega final. So let's see here. I naught is I1. And omega naught is omega 1, and that's going to equal, and here we have to be careful because both of the disks are rotating, so the total I final is going to be I1 plus I2 times omega final. So solving for omega final, we see that it is the initial angular momentum of the first disk divided by the total rotational inertia of the two disks together. And this is kind of the angular equivalent of an inelastic collision. Remember, we would get m times v, m initial times v initial, divided by the total mass of the system is going to give us v final. So this would be like one railroad car that's moving at speed v collides with a second railroad car at rest, and they stick together. What is their final velocity? All right, so this is like a rotational collision, rotational inelastic collision. Another example where you would see this happening is a classic example. We've got a merry-go-round, and we've got a kid of mass m sitting on the merry-go-round. And let's go ahead and say that this merry-go-round has radius r, and this merry-go-round has mass big M. And initially, it is rotating with some omega naught. Now, this person who's originally in the very center of the merry-go-round decides that they're going to walk from the center all the way to the outside. So now we still have the merry-go-round, but that mass little m is sitting at the edge, a distance r away from the axis of rotation. So the rotational inertia of this system has changed. All right. Initially, essentially, it was just the merry-go-round that was rotating. The person in the middle, yeah, true, they have a rotational inertia, is equal to little m times little r squared. In this case, little r essentially is 0. So this would be 0 to start with. So it's just going to be I for the merry-go-round times omega naught. That's the initial angular momentum. Now the person walks to the outside. Quick discussion of why the net torque here is 0. The merry-go-round applies a torque to the person. The person applies an equal and opposite torque to the merry-go-round. So again, we see that the net torque is 0. So if the net torque is equal to 0, then L naught is equal to L final. Okay, so let's see here. Initially, it's just the merry-go-round that has momentum. So that's going to be I for a disk. Let's see, 1/2 mass of the merry-go-round times r squared times the omega initial. And then finally, we have the merry-go-round and the person's rotational inertia combined. So the merry-go-round, 1/2 big M times r squared, plus the person, which is just m times big R squared, times omega final. And again, if we're looking for omega final, we're going to divide. So we end up with 1/2 big M big R squared omega naught divided by the total rotational inertia of the system after the person moves. And there we go, omega final, piece of cake. Okay, so look for the net torque to be 0. If the net torque is 0, bam, conservation of angular momentum, piece of cake. Another classic example that we've all seen in the Winter Olympics, you've got an ice skater, and this is a very complex picture of our ice skater. This ice skater has his or her arms outstretched, and she or he is rotating with some omega naught. And then they bring their arms in, and they rotate much faster. When they bring their arms in, what did they do? I went down. So we have, from there to there, I decreased. So if I decreased, from there to there, omega is going to have to increase. Because again, there's no external torque acting on the system. All the person did was they brought their arms down. What did that do? It changed I. If you decrease I, you're going to increase omega. So by bringing all that mass in, omega goes up and they spin faster, crazy fast. All right? So again, look for this. And if that's true, L naught is equal to L final. Breaking it down, I naught, omega naught is equal to I final, omega final. Okay? So this would be the total rotational inertia of the system before a change happens, and this is going to be the total rotational inertia of the system after the change happens. Okay? So we're going to work all sorts of fun and interesting problems based on this principle. But you need to, again, I'm belaboring the point here, you need to make sure that the net external torque is 0. Okay? That is the condition that's required here. And when this is happening, energy is not necessarily conserved. Okay? In most cases, in fact, energy is definitely not conserved. Okay? So this is the key to solving problems like this. All right? Thanks. See you next time.